You just installed a brand new commercial water pump, but up on the 5th floor, your guests are dealing with a weak, sputtering shower. The most common reason for this failure is the number printed right on the side of the pump's box. Usually, that's the maximum flow or maximum head specification. Manufacturers calculate these maximum numbers in a perfect laboratory setup. They test the pump with zero pipe resistance, measuring the water as it pours straight out of the housing. But your hotel is not a perfect laboratory. You are pumping water up multiple stories, fighting gravity, and pushing through a maze of pipes and elbows to reach dozens of rooms. Grabbing the pump with the highest maximum numbers saves time at the hardware store, but because those numbers ignore the physical reality of your building, they guarantee weak pressure and guest complaints during your morning rush. To avoid those complaints, some project managers swing to the exact opposite extreme. They design the system assuming every single room in the building will turn on the shower at the exact same second. Designing for that scenario forces you to buy oversized, industrial-grade pumping equipment. That requires a massive upfront capital expense for capacity you rarely use. And the spending doesn't stop after installation. Pushing an oversized pump every day drives up your ongoing electrical bills, forcing you to pay for unused capacity year-round. So the core dilemma is how to look past both the marketing hype and the fear of failure. You have to calculate the actual water capacity required for your specific building's layout. Finding that mathematical middle ground is the only way to protect your operational budget while still delivering a reliable shower to every guest. To find that middle ground, we evaluate commercial hotel water systems using what are called rated specifications. This diagram compares the two metrics side by side. While maximum specs show output with zero resistance, rated specs measure the water output under actual working conditions, like pushing water up 30 meters of pipe. For example, look at the YCB 700 pump. It promises 5.8 cubic meters per hour under maximum ideal conditions, but under a realistic rated load of a 30-meter head, it delivers 3.5 cubic meters per hour. Ignoring the marketing labels and sizing your system based on those rated specs gives you a highly accurate baseline for how the pump will actually perform in your hotel. This waterfall chart illustrates the concept of pressure loss. To get water to your guests, the system has to fight the gravity and friction inherent in your architecture. Let's look at exactly what eats away at your required pump pressure. The first major physical hurdle is the vertical height of your building. The formula is simple. Every single meter of upward travel destroys 0.1 kilograms per square centimeter of pressure. Pumping water 15 meters straight up instantly costs you 1.5 in pressure. The second hurdle is horizontal distance. Water loses momentum as it drags along the inside of long pipes running down your hotel corridors. For every 10 meters of flat pipe distance, friction destroys another 0.1 in pressure. Finally, we have to account for the plumbing layout itself. Every time water slams into a corner to change direction, you lose energy. Every 90-degree pipe elbow strips away another 0.1 in pressure. If you have 5 elbows, you lose 0.5 before hitting your final target at the faucet. This creates a direct architectural trade-off. You must either invest in a pump with a significantly higher rated head to defeat these specific physical penalties, or accept that your top floor guests will have weak showers. Once you map out the physics of your pipes, you have to account for the mathematics of human behavior in a commercial property. We estimate simultaneous peak water demand using what the industry calls the 60-50 rule. The first half of the formula assumes a standard baseline hotel occupancy rate of 60. If you apply this rule to a 16-room boutique hotel, the math shows you realistically only need to power about 5 simultaneous outlets during the morning rush. Accepting the minor statistical risk of a freak usage spike allows you to purchase a smaller, highly efficient pump. It keeps your costs tight and avoids commercial overkill. This scorecard maps out the exact hardware needed for 2 common building sizes. The boutique profile covers 15 to 20 room properties facing standard pressure loss limits, targeting 5 simultaneous outlets. A targeted mid-capacity pump like the YCB 700 matches this profile perfectly. It maintains 3 kilograms per square centimeter of pressure across those 5 outlets. This is highly cost-effective. But if you add a high-demand spa facility or build a new wing later, this pump instantly becomes a bottleneck. The right side shows the mid-size profile for 35 to 45 room properties. These buildings have heavier vertical pressure loss conditions and support roughly 12 simultaneous outlets. For this volume, you need to upgrade to a high-capacity unit like the YC-SK 1.5 to safely maintain pressure across the expanded network. These high-capacity units draw more power and require a higher initial investment, but they are non-negotiable for medium-sized hotels where top-floor guest expectations are strict. Moving forward, you have to stop reading the maximum performance numbers printed on the outside of commercial water pump packaging. A reliable guest experience is built on surviving the reality of pipe friction and vertical lift, not on surviving perfect laboratory conditions. Before you shop for hardware, measure out your physical blueprints. Map out your required pressure limits using the exact height, distance, and elbow formulas for your building. Combine that physical pressure mapping with the 60-50 occupancy rule. This gives you the exact metrics needed to perfectly right-size your water system. Let the mathematical reality of your specific layout dictate your system hardware. You will protect your operational capital and guarantee the perfect shower for every guest.